On analytic function. In this video, we are going to study about the property of analytic function. So here, let f of z be an analytic function, and we have to prove that dou square by dou x square plus dou square by dou y square of the modulus f of z whole square. We have to prove that it will be equal to 4 into modulus of f dash of z whole square. First, we will take this LHS part. Then we have to prove that it will be equal to 4 modulus of f dash of z whole square. So let's begin. So first I may take assumption let f of z will be equal to u of x comma y plus I into v of x comma y. Here u and v are function of x comma y. Then in our assumption, the given problem, if f of z is an analytic function. So in the problem itself, they have given assumption that f of z is an analytic function. If it is analytic, it will satisfy the CR equations. CR equations will be ux equal to vy and uy equal to minus vx. And also these two functions u and v are harmonic. Since if you are harmonic, it satisfies the Laplace equation. Uxx reference u dou square u by dou x square. Uyy means dou square v by dou square u by dou y square. As same as for the vx vy, vxx vyy. So uy represents dou u by dou y. Vx represents dou v by dou x. Okay. So on the next, these are the assumptions. And let me take a part. Modulus of f of z will be equal to modulus of, see, if I am taking u plus iv. So what happens? A complex number means we will take a square root and we will square each of the term. So this will be the value for modulus of f of z. If I bring the square root to the side, it becomes modulus of f of z whole square equal to u square plus v square. Then what we need to find? We need dou by dou x square plus dou square by dou y square of modulus of f of z whole square. So we know how the function modulus of f of z whole square is. Here it is. Now we need to, if I take this term now, how it will be dou square by dou x square of f of z whole square plus dou square by dou y square of modulus of f of z whole square. So first we will find this part and then we will find the next one, and finally we will add up the both to get this LHS part of this given property. So let me differentiate this function with respect to x. So simply how it will be, we know that u is a function of x comma y and also v is also a function of x comma y. So if I differentiate, see, x of u square plus v square, simply u is a function of x comma y, yeah. So while differentiating this function, how it will be dou x u of x comma y whole square plus dou by dou y of v of x comma y by v square. So if I differentiate this, you will get 2 u of x comma y into, with respect to x, then you will differentiate this function u by dou x plus 2 into v of x comma y into dou v by dou x. So here we used to write 2u ux plus 2v vx. So finally we get this part. In a similar manner, while we differentiate it again with respect to x. So if I am differentiating this term with respect to x again, what will happen? I will differentiate this function with respect to x. So simply while I am differentiating this function 2u alone. So let's see here 2 will be a constant and then it will be of dou x by ux. So on the next, 2 will be a constant value. If I differentiate this function, it will be in the product rule, u dot v. So how it will be u v dash. So u v dash. Here u is u and v is ux. So v dash represents uxx. Again, I will differentiate this function. That means dou square u by dou x square plus v dash u. So u v dash v u dash. So what's the final data I will getting? Uxx plus ux. Sorry, I may write like this. So similarly, xx plus v ux whole square. So if I differentiate this function alone, I am writing for u and uxx alone. So I may get like this. If I differentiate this function with respect to x, 2v So 2 will be a constant. So we have to differentiate this function vx. Then I will get the value of again u dot v u. Here it is v u v dash. So vxx. Then vx into vx. So finally we will get 2 of vxx plus vx whole square. So while adding both, we will get this term. 2 is common for both, so I'm taking 2 as a constant. Ux square is here, vx square is here, and uxx here, vxx here. So therefore we get this equation 3. Now we are doing a same procedure for the same function with respect to y. I will get the value of dou u. First of all, we will differentiate this function with respect to y first. So here, if I am taking f of z, I know that whole square it will be u of x, u square plus v square. So if I differentiate with respect to y first, so I will get the value of 2u y plus 2v y. So if I differentiate this again, I will get this term. We have to differentiate this with respect to y again. So it will be, what do you mean? Here it will be dou by dou y of f of z whole square. So if I'm differentiating this once again, it will be a second order derivative. So by using a product rule, first I will differentiate this 2u y with respect to y. 2 will be a constant, so dou y u y will be there. So if I use the product rule, I will get the value u y plus u y. The same similar manner what I have did for the variable x. So similarly, if I take this alone for the function vy, I will take 2 as constant and I will differentiate this function vy. I will get the value as vyy plus vy. So vy into vy it will be of vy whole square. Uy into uy it will be of uy whole square. So finally, while adding both, I will get this equation number 4. So this is what they have given. And finally, already in the previous slide, I have find the value of dou square by dou x square with respect to the function modulus of f of z whole square. And with us, I am as equation 3, and here I am getting the with respect to y on equation 4. So I will add up the equation number 3 and 4 to get the final result. So adding the equation 4, 3 and 4, I will get this result. And we know that u and v are harmonic. So it satisfies the Laplace equation. Laplace equation will be uxx plus uyy will be equal to 0. So here, if I take here uxx is here, uyy is here. So u is common for both the term. I may take u as a common term. and I may use to write uxx plus uyy. Similarly, vxx is here, vyy is here, and both term which carries a constant as v. So we can take v as common term, and we used to write vxx plus vyy, it will be equal to 0. So by this, I am rewriting on the next step. So it will be 0 according to u and v are harmonic. So on the next, I will get the remaining terms alone. So what I need to prove here, if you go for the previous slides, what we need to prove? We need to prove 4 into modulus of f dash of z whole square. So let's start here. I'm getting this as result, and if you see the Cauchy's equation, uy will be equal to vx. Ux will be equal to vy, uy equal to minus vx. If I am differentiating these terms, what will happen? So it will be like this. I'm just squaring the equations. These are the CR equation. I am squaring it. It will be of uy square equal to vx square. Here it is. U square, ux whole square and vy whole square. So here it is. But these two equations are same. If these two equations are same, now if I add the equations similar manner, we get uy whole square plus vy whole square can be written as vx whole square plus ux whole square. So see here, ux u ux square vx square. So ux square is here, ux square vx square is here. If I am adding both, this will be equivalent to the remaining terms as a sum. So what we can do on the next step, we used to write the term here. Instead of ux, we may write vx square. What we need, ux alone, ux and vx means you have to replace the remaining y terms with respect to u. Uy can be written as vx square. So we will get 2vx square, and we used to write vy square. Vy square is ux square. If I write ux square, then here it will be of 2ux whole square. So while adding both, I can take the 2 was common from this both terms, so I'm getting 4 here. So finally, we used to say modulus of f of z will be square root of u square plus v square. If I'm taking the derivative of the given function, then if I take the modulus means, we can say that it will be of ux plus, see, f dash of z will be ux plus ivx. Okay, if I'm differentiating with respect to x. So if I'm taking modulus now, it will be ux square plus vx square. That's how we get the remaining. So it will be equivalent to the modulus of f dash of z whole square. So finally, we proved the LHS will be equal to RHS part. So proved, it has been proved using the Cauchy-Riemann equation, harmonicity of u and v, and we have used the chain rule and the Laplacian identity. Finally, it is hence proved.